Hello everyone. So remember yesterday we talked about Newton's second law. So tonight we're going to talk about the first law and the third law. But first this. So this brings us to Newton's first law. So Newton's first law tells us that in order for you to change your motion, a force must act on you. And the same goes for if you're already moving. So let's say you're moving at, I don't know, some speed. In order for you to change your motion, there has to be some sort of external force that acts upon you. If you're standing still, an external force can come along and apply a force on you, and it'll change your motion. Now you have to apply this external force because everything with a mass has a property called inertia. Inertia just means that the universe doesn't like change in motion. So this means that if something is resting, it'll keep resting, and if something is moving, it's going to keep moving. Unless, of course, there's an outside force that acts on it. So you've all felt inertia before. We usually feel it best when you're interacting with something else that also has inertia. You're driving in the car and you have to slam on the brakes. The car stops no problem, but you keep going because you have this property of inertia. If you have a seatbelt on, it'll apply an external force on you to help you slow down with the car. Another example of this is our friend from the opening video. The longboard under his feet stopped, but his inertia kept going. His inertia prohibited him from stopping with his longboard, and because there was no external force like a seatbelt to stop him, he fell in the grass. I'll leave this talk of inertia with this. See if you can figure it out using this idea of inertia. So now we're going to move on to Newton's third law. Newton's third law says that every force is paired with an equal and opposite force. So, for example, let's look at a fish that's swimming in the water. So, in order for a fish to swim through the water, the fish must push on the water. He must swing his tail back and forth and push on the water. And a result of the fish pushing on the water returns the favor and pushes back on the fish. So let's look at a free body diagram in this situation. We're going to represent the fish with a single dot, and we want to draw an arrow when the fish kicks its tail. And we're going to call this force the force of the fish on the water. The force of the fish on the water. Now, the equal and opposite force says there's an equal force going the exact opposite direction. And this is the force of the water on the fish. So because the fish pushes on the water this way, the water pushes back in the opposite direction and the fish is propelled forward. Now, one thing that you have to remember is that force vectors are not motion. They are not the same thing. So just because they're equal forces, it doesn't mean that the motion of the water and the motion of the fish is going to be the exact same. So from our free body diagram here, let's set up an equation. We know that the force that the fish applies on the water must equal the force that the water applies on the fish because of Newton's third law. Now remember, Newton's second law says that F is equal to ma. So let's go ahead and plug this in. So now we have the mass of the water times the acceleration of the water is equal to the mass of the fish times the acceleration of the fish. So now let's do a little qualitative analysis. So if we compare the masses of the fish, the small little fish, and all of the water that it needs to push out of the way, it turns out that the mass of the water is absolutely immense compared to the fish. Okay, so we have a big mass, and that means that the mass of the fish is really small. Now, because these forces have to equal out, it means that the acceleration of the water is going to be really small. So if this is really big, and this is really small, and this is really small, then that means that the acceleration of the fish has to be really big. So the fish kicks its tail around. The fish kicks its tail around, and all of these little water particles are accelerating at a very small rate. But there's a lot of little particles, so the mass is huge compared to the fish. Okay? So we have a big mass, but a little acceleration. And that's going to equal the little mass of the fish, resulting in a very large acceleration of the fish, and the fish is able to swim away. So we'll play with these ideas a little bit more in class tomorrow, and we'll see you then.